Hi all, and welcome to the Medical AI Lab group session. Today I'm delighted that we have Emma Chen from the lab giving us a presentation on the very exciting AlphaTensor work that came out earlier last week. So without further ado, Emma, take it away.
Thank you, Pranav. So today I'm going to talk about AlphaTensor. Before I start, I guess the first question everyone who has not read the paper yet might be wondering, what is AlphaTensor? AlphaTensor is a way to discover efficient algorithm to speed up matrix multiplication by treating the algorithm discovery process as a game. And it applies reinforcement learning on this game to find the optimal algorithm. So today I'm going to organize my presentation into 4 sections. I'm going to talk about the motivation of AlphaTensor. So why do we even care about speeding up matrix multiplication? And then I'm going to talk about the algebra or the mathematical foundation of why AlphaTensor works. So I'm going to talk about the matrix multiplication. I'm going to mention that the decomposition, which is the key part of this algorithm discovery process, and how we can formulate a single player game from this decomposition and train a reinforcement learning algorithm to learn how to do the decomposition. And then I'm going to go into the detail of the training process. And finally, I'll highlight 2 very interesting results. But today I'm going to mostly focus on the math and the training. And that there's so many exciting results, but I think it's easy to just go over them offline for everyone. So why do we even care about efficient matrix multiplication, or why multiplication specifically? It's really because multiplication is slow compared to addition. So imagine we are doing a addition simply as 2 plus 5 in a computer. I mean, everything is binary, so we're going to do this binary addition in a computer. What you're seeing here, you can imagine that each of the line, can everyone see my arrow?
Yes.
Okay, each of the line is, imagine that that's a wire, and then you have this FA, I think they're called full additor, or just treat them as some magic components, electronic components. When we do a addition, what we have is the number in binary format, and then we're going to do a binary addition using the adder. All of these can be done in parallel, which means even though I have 4 bits here, I just need 1 cycle to achieve the addition result. However, in order to do multiplication, we have to do a series of addition and bit shifting to achieve that. So going back to the example of 2 and 5, instead of doing 2 plus 5, we're going to do 2 multiplied by 5. We have the binary here. And then we're going to, I mean, this detail is not important, but what I want to show is that we will have to go through a series of addition, shifting, addition again, in order to achieve the final result. So the key takeaway is multiplication requires multiple cycles, and compared to addition, it's just more expensive. This is why we want to speed up computation by reducing the amount of multiplication we need to do and replace it with additions. Looking at this example, a squared minus b squared can be translated into a plus b times a minus b. So this is a formula we're all very familiar with. The reason why this is an efficient way to compute a square minus b square is because instead of having two multiplication, we have only one multiplication. And then we replace the other multiplication with two addition. So in this way, even though we are adding more additions, we're still being more computationally efficient. So now, how are we going to speed up matrix multiplication? This is a simple example of matrix multiplication I actually get from the paper. We're all familiar with matrix multiplication. In order to get the final result, we have to multiply matrix element row by column, row by column, row by column, row by column, and row by column again. So to do this simple matrix multiplication, we'll actually end up having to do 8 multiplications. So similar to the idea of replacing a square minus b square with a plus b times a minus b, can we come up with a way to reduce the amount of multiplication we have here and replace it with some addition? So here I can propose 7 intermediate value. They are some addition, but each of them only contains 1 multiplication. And I can show that the C1, C2, C3, C4 value from the final matrix is actually a linear combination of these 7 intermediate value. And in the end, it only cost me 7 multiplications to achieve the matrix multiplication. So now the question is, how do I even come up with this 7 intermediate values? And how do I know what combination I should use to get C1, C2, C3, and C4 from the 7 intermediate values? Before I go into the way to do that, I'm going to introduce this 3D multiplication matrix that is also mentioned in the paper. So what is this matrix? Basically, it says every matrix multiplication can be represented in the form of a 3D matrix, a 3D matrix. So it's just a representation. What it is for each dimension, let's look at the C channel, the C1 channel here. For each dimension, for each C dimension, we'll have a 2D matrix with 1 or 0. So the darker purple here represent 1, and then the greater purple color here represents 0. And this 1 and 0 corresponds to the multiplication, the element pair, the element-based multiplication we need to do in order to get C1. Let's call this matrix Tn, or I think it's tau n, Tn. And we know that this matrix can be decomposed into a summation of a series of 3D matrix. And each 3D matrix can be further written as the outer product between 3 vectors. And if anyone forgot how outer product works, this is a screenshot from Wikipedia. Anyone who's watching the video can pause here and read this piece of information. But I'm gonna skip here, and I'm gonna assume that doing a outer product of this 3 matrix will result in a 3D. An outer product of these 3 vectors will result in a 3D matrix. But why am I doing all this peculiar process of decomposing the original 3D multiplication matrix into a summation of a series of 3D matrix, and then further decompose each matrix into the outer products of 3 vectors. This is because each of these vectors are very useful for us to come up with the intermediate value and the combination of the intermediate value that will result in the final elements in the product, in the matrix multiplication result. So now I'm going to show you how U, V, and W is going to generate the intermediate result, and then how we're going to combine the intermediate results into the final element. So let's forget about the W vectors here. Let's look at the U and V. In order to get M1, we can see that there is a corresponding between U, V, and M. The way it works is you can treat this as a mask, or if the element is not 1, if it's 2 or 3, then you can see it as a mask, but multiplied by 2 or 3 or some scalar. But let's treat this as a mask for now. This, if we mask it on the vector A, it will result in A1 and A4. And I'm going to do a summation of whatever elements that are remaining after being masked by this vector. Similarly for V, if I mask the B vector with 1, 0, 0, 1, I'll have B1 and B4 remaining. And I'm going to sum them together. And then I'm going to do the multiplication between the sum of A1 plus A4 and the sum of B1 plus B4 to get my first intermediate value, M1. Similarly, I'm going to do the same thing for M2. I'm going to mask A1. Sorry, I'm going to mask the A vector, and I'm only going to have A3 and A4 remaining. I'm going to mask the B vector, and I'll only have B1 remaining. And then to get M2, I'm going to multiply the results of A3 plus A4 times B1. Same for M3 and M4, M5, M6, M7. So you get the idea of how to calculate the intermediate value just from the U and V vectors here. After I have the intermediate value, the next thing I need to figure out is how to combine them so that I can receive the final elements of the matrix multiplication result. So to get C1, we're going to look at this W vector. You see that similar to using U vector to mask A, or using V vector to mask B, we're now using this W vector to mask the M vectors here. So here I have 1, 0, 0, 1, negative 1, 0, 1. So it's not really a masking, but it's similar to masking. But basically it's element-wise multiplication. I have M1 times 1, M2 times 0, which is masked to 0, 0 again, M4, and then M5 times negative 1, which is minus M5, and then M6 is masked by 0 again, and then M7 is 1. So this is how I get C1, by summing up everything together after I masked out my M1 vector, my M vector. And it's the same thing applies to C2 and for the rest of the elements. So this process shows us how the reason why we want to decompose the original 3D matrix is to get this U, V, W vectors in order to find the intermediate values and to find the final combination of the intermediate value to reach the elements in the final multiplication result. So a recap here, given a matrix multiplication, I'm going to find a way to decompose the 3D matrix the 3D multiplication matrix. Once I'm able to decompose this matrix, I'm able to formulate, I'm able to find the U vector, the V vector, and the W vector, which will correspond to the intermediate value and the way to construct the final value. And the number of intermediate value here will correspond to the number of multiplication I need in total in order to reach the to get the final matrix multiplication result. Because if you look at how every intermediate value is calculated, each of them only requires one multiplication, and then no multiplication is needed at all to calculate the final elements. So in the paper, they provide an algorithm which is basically describing this process of decomposing the matrix, the 3D matrix, and then calculate each element by masking the A and B vector with U and V. So now, how do we optimize the process of this decomposition? This is where reinforcement learning is used by the paper by treating this composition process as a single player game. Before I go into the way the game is formulated, I'll briefly mention what AlphaZero is. So this is a very brief description I found from the DeepMind website. It's basically a system to teach itself from scratch to play game. So it does not train on any human players data. It just trained by playing the game on its own. So game playing is the keyword to use AlphaZero. That's why AlphaTensor formulate the questions of finding the matrix decomposition into a single player game. In this game, the goal is to find a way to decompose the 3D matrix, the 3D multiplication matrix, into a summation of R 3D matrix or R outer product, with R being as small as possible. Because remember, R is associated with R corresponds to the number of multiplications we need. So the smaller the R, the fewer the multiplication we need, element-wise multiplication we need, which means the computation will be less expensive. So in this single player game, the initial state will be Tn, which is the original 3D multiplication matrix that we want to decompose. At each step, the player will select a set of U, V, and W vector. And the new state will be the original, the previous 3D matrix minus the outer product of these selected outer product of UVW. So this is a 3D matrix, this is a 3D matrix, and it will result in a new 3D matrix. And in order to avoid doing this decomposition endlessly, we're going to restrict the maximum number of steps that is allowed to finish the game. And the goal for the game is to reach a final state where we'll get a 0 and with as few steps as possible to reach the final state. So how do we encourage the players learn to use as few steps as possible? The way we do it is to use a negative reward for each step. So the more steps you get, the final return is going to be smaller. And also we mentioned that we do set a limit on the maximum number of steps the player can play, which means that sometimes it will fail to find a decomposition at the end. So the game will just give a negative reward if at the end of the maximum steps, the player does not reach a zero state. So now we're going to talk about the neural network. This is a very simplified version of what the network is. The network takes the input of the network will be the current state, which is the 3D matrix we want to decompose. The output of the network there'll be two output of the network. One is a policy. The policy will give a distribution of the potential action to take at a given state, and we will sample the actions from this distribution. It will also, the second output is a value which will estimate the future return from the current state. So the neural network is trained from either previously played game or some generated synthetic data. So what is this generated training data? So we know that it's hard to do matrix decomposition, but the reverse is actually very simple. If I am given a random set of vectors, then I can calculate the outer product, and then I can add them together to do the reverse process of decomposition to get the initial 3D multiplication matrix we want. So by just randomly sampling this factorization, this U, V, and W will easily reach the final multiplication matrix that we originally want to learn to decompose. And a pair of these tensor and factorization will become a training data for the neural network to learn. So once the neural network learn from these data, it's going to update the model, and then we can start playing the game. The way it works is the game is going to start from the target 3D matrix we want to decompose. At every step, I'm going to use a Monte Carlo tree search to find the next step to take. The next action to take for each step. So what is Monte Carlo's tree search? So instead of going through, so we have a search tree, and instead of traversing the whole tree and finding every node, I'm going to sample a subset of the tree. And the way it works is I'm going to randomly sample, not randomly, I'm going to sample the actions based on the policy. I'm going to take the action, and I'm going to continuously play this game until I either reach at the end of the game, which means I reach a 0, or I reach a state that I have never explored before. So by doing a lot of simulation at each step, I will actually reach a optimal step to take an optimal action to take just for this step. So I'm going to repeat it again. So at each step, I'm going to run a lot of simulation. And after all this simulation, I will have the optimal action to take for this step, and I'm going to take that step action and reach the next step. And then the cycle repeats. I'm going to do simulation, find the action to take for the next step, take the action, and then go to the third step continuously until the game ends. So when the game ends, the played game itself would become a training data to train the model in the future. So this is the reinforcement learning part of AlphaTensor. The last thing I'm going to quickly go over is some interesting result they mentioned in the paper. The first one that is pretty interesting is they have a table and they show that by using AlphaTensor, they are able to either discover algorithms that is as efficient as the current state of art, or they're even able to improve algorithm for calculating these matrix multiplication. And the one example they highlight is this algorithm that was discovered 50 years ago, and they're now able to improve it even further. And the next interesting result I want to highlight is that AlphaTensor can actually find efficient algorithm that is tailored to a specific hardware without knowing, without prior knowledge of the hardware. And the way they do it is to encode the hardware constraint into the reward function for AlphaTensor. So here, it will use the runtime benchmarked on the certain target hardware and use that as a penalty during the training. Okay, so a quick summary of my presentation. We talked about why AlphaTensor wants to work on improving multiplication, because multiplication is expensive. And we talked about how we can improve multiplication by substituting certain products with addition. And the way to do it is to do a matrix decomposition to get the UVW vector that will allow us to compute some intermediate value, and then a combination of the intermediate value with less multiplications needed. And the way AlphaTensor works is it treats this process of discovering the decomposition as a single player game. And I use AlphaZero to learn the policy. So that is my presentation. Thank you.
Awesome. Thanks a lot, Emma. That's a wonderful presentation.